Okay, so shall we start today's class? Well, so let's now try to recall what are the topics that we covered in the previous class. We learned 3 different protocols in the last class. We learned about a protocol called collision avoidance time allocation protocol, which is called as CATA, and then we learned content-based protocols with reservation mechanism, especially HRMA, and also the soft reservation multiple access with priority assignment protocol. And basically these protocols come under the category of contention-based protocols with reservation mechanisms. So what do we mean by reservation? We are now trying to allocate a particular bandwidth or a channel for the nodes by having some reservation mechanisms. Okay, so we have been looking at different methodologies, and the last one that we talked about was a soft reservation multiple access with priority assignment, and we understood how priority can be fixed while reserving the channel for the particular nodes. Now today we will look at another protocol, a very interesting protocol called 5-phase reservation protocol, which is also called as FPRP. Alright, this also comes under the category of contention based protocol, and it also adopts certain reservation, and the reservation basically takes place in 5 phases. Oh, sorry, I haven't still loaded it. You should have told me. Yeah? Are you able to see the screen? Alright. So this is a 5-phase reservation protocol. Alright. So what is unique about this protocol is what we need to look at it. And we also need to look at how this 5-phase reservation protocol is different from all the other protocols, and what are the advantages of using this protocol, where can we apply it, okay, and what are the typical problems that it is trying to solve. We need to look at that. Okay, now this 5-phase reservation protocol is a single channel time division multiple access protocol. That means the channel is divided into time slots, alright, and then you try to reserve a particular time slot, and then you are trying to use the channel for the data transmission. Okay, so the contention of nodes with reference to the channel is based on occurring the time slots. Okay, so there is a time frame available, alright, and it is basically divided into slots, and they try to acquire a particular time slot for them to do the data transmission. Now in order to acquire it, alright, we need to do the reservation. Okay, so that reservation basically takes place in 5 different phases or stages. That's, we call it as a reservation phase, collision report phase, reservation confirmation phase, reservation acknowledgement phase, and then we have a packing and elimination phase. Now we are going to quickly look at what are these phases and how it's basically helping my reservation protocol, and why do I need such a 5 different phases to handle, a reservation. Alright, all that we will look at it. Okay, and the basic assumption that we may have to have for this particular protocol is that all the available nodes share a global time. Okay, probably that means we are doing a synchronization of all nodes. That's what it means. So we are having a node synchronization. Okay, all right. Now let's try to understand a little bit better. Okay. This is the frame structure of this protocol. Now what do you look at it? You have code words which shows RF, IF, am I right? So when you look at this frame, basically shares RF, IF and so on, and then an RF, and then followed by certain IF frames. Now what is RF? RF stands for a reservation frame, alright, and IF stands for information frame. So that means during the RF frame, the reservation basically takes place, and during the IF frame, the informations are being exchanged. Clear? Now we will find in this particular slide there is one RF frame followed by multiple IF frames. Am I right? So that means you are trying to do a reservation, and when you are trying to do a reservation, you are trying to handle it for different frames of different size in terms of information. Alright, and then you continue with your RF and then with IF. So let's now quickly look at in detail what are those RF reservation frames, how it's composed of, because we always studied that each frame is divided into slots. Alright, so try to recall that these frames, even though you have multiple frames here, RF frame you have, which basically will also comprise of few slots, am I right? And then IF frame will also have few slots. Alright, so that's how it is partitioned into based on the time division multiple access mode. So if you look at RF, you have here that is divided into slots. Now how many slots? Here it has been divided into n slots. So you have RS1, RS2 and so on up to RSn slots. And then information frame is also divided into slots, which basically that says that okay, you are trying to send particular information during this slot. So it says IS1, IS2 up to ISN slots. So you have n slots for reservation, n slots for information. So that means if you are able to block one for your node, let's say RS1 slot, let us assume if first node takes the reservation in RS1, that means it can send it during the IS1 slot. Are you getting what I'm saying? Let's assume the Xth node blocks RS2, that means Xth node can send the information at the IS2 slots. Okay. Now in detail if you look at it, these slots are still divided into cycles. Okay, we call it as a reservation cycle 1, reservation cycle 2 and so on up to reservation cycle n. Alright, so you have slots, but each slot is slightly internally divided into time slots, which basically we call it as a reservation cycle. Alright. Okay. Now during a particular reservation cycle, it's still divided into 5 different phases. Are you all getting what I'm saying? And that's where we have RR, CR, RC, RA and P by E. Now what is RR? We learnt it here. It's a reservation phase. Am I right? This is the reservation phase. Are you following my cursor? Okay. And then you have CR, which is basically a collision report phase. And then you have a reservation confirmation phase. Then you have a reservation acknowledgement phase. And then you have a packaging or packing and elimination phase. Now you understood how the slots of the reservation is divided into different cycles, and each cycle you have certain phases. There are 5 different phases. Okay, so it's something like this. We will try to understand first these phases, and then we will try to roll back to figure out how it really helps in your cycle. So the cycle need not be n times based on the number of slots. Okay, it can be m time. That means the cycle number of cycles varies. Okay, it need not be necessarily equal to the number of nodes in a particular network. Okay, now let's look at what is reservation phase. Alright, reservation phase is a phase in which someone wants to say, okay, I wanted this slot, alright, for me to communicate to this particular node. Alright, so it's something like a reservation request. Are you getting what I'm saying? Alright, now this reservation request is basically broadcasted. Alright, so to whom? To the next one hop. So you try to do a little bit of broadcasting to all the networks or all the nodes at a one hop distance. Okay. Now based on the reservation request, you might get a collision report. Alright. What is a collision report? You are sending a reservation data for which you are not getting an acknowledgement. On the other hand, you are getting a collision report. That means your packet is somewhere down the line dropped or it is lost. Okay. So when you understand that there is a collision that has taken place, then you keep yourself idle. You don't try to send the packet because you don't try to reserve anything for that. Are you getting what I'm saying? If not, alright, if let's assume that there is no collision report, then it means that you are able to successfully do a reservation, and therefore you will receive something called as a reservation confirmation. Now who sends the reservation confirmation? Is it the sending node or the receiving node? No, not the receiving node. It is the sending node. Alright, the sending node says, oh, hi guys, I have blocked this for me because I have not received any collision report. Are you getting what I'm saying? And then meanwhile, the receiving also is all visibly looking at, okay, the reservation was confirmed, and now he is sending the acknowledgement back saying, okay, I'm ready, you can shoot your data. Are you all getting what I'm saying? So based on your reservation, let us assume that you are able to, please look at this slide. Let us assume that you are trying to reserve a slot in this particular cycle. Okay. Now if you are not able to, alright, then probably go for the next cycle and make the same attempt. That is also not working, then you look for a next cycle. At that cycle you try to basically do a reservation request and try to reserve the channel for you. Are you getting my point? So the objective is to reserve the channel. So when you do that, now let's assume that we are now trying to do it for R as n. That means we are trying to reserve the slot for the nth point. So that means you are able to reserve it for the is nth frame. You all clear? Now you may probably wonder why all this 5 phases and why did we do all that? We earlier had a simple scheme by say RTS, CTS, and then you went it on. Now what is this and why do we require? Now let's look at this example. Now you'll be able to understand it better. I have 10 nodes here. Is it all okay? And the node which has been doubly circled is the transmitting node. Assume that. Okay. So what happens? The transmitting node basically sends the RR packet. Assume that straight line refers to RR packet, dotted arrow refers to RC packet, which is called as confirmation packet. Let's assume CR, alright, which is the collision report packet, which has a little hashed line, and then a line with a dot. Let's assume it's an acknowledgement packet. Now take a typical case of this network. This is a mobile ad hoc network and I have 11 nodes altogether, and there are 3 nodes who would like to transmit the packets. Those are number 1, number 7 and number 9. Okay. Now let us assume, how does the RR reservation takes place? It basically puts it off, sends it. Okay, so it basically broadcasts. So you find one broadcast for 4, it broadcasts for 2, it broadcasts for 3. So RR packet is gone. Alright, there is no collision here, and therefore there is no collision report packet, which is called a CR packet, and therefore I am now able to send the reservation confirmation packet. I have now blocked the channel. The objective is to block or to reserve the channel. So now I am now trying to send the reservation confirmation packet, and then I get a response, which is a reservation acknowledgement. This is a very typical scenario, so simple scenario. So it's good to understand it better. Now let's look at this case. This case 7 and 9 wanted to now send the data packet. So this broadcasted, so you broadcast to 8 and also to 11. 9 also now tries to broadcast it because it also wants to transmit the packet. So it sends to 10 as well as to 11. Now what's going to happen? Collision takes place. Collision takes place at node 11. Therefore you find 11 sends a collision packet, report packet, both to 7 and 9. So that's what you see here. Are you getting it? So when it sends to, let's assume 2 nodes, then you say, collision has taken place, and therefore you don't go for reservation confirmation, and then you don't go for the next packet. So what happens? Both of them don't try to reserve it, because at the same time you are able to see a collision. Okay. Now how do we put it? Alright, when we say 7th node, alright, tries to broadcast for a 1 hop, it tries to probably ascertain for nodes up to 2 hops. Am I right? Are you able to follow me? When you try to send a packet from 7, do a reservation, even though you are sending it for 1, for a 2 hop distance you are able to check whether there is a collision. Am I right? Are you getting what I am saying? So in your book, if you read, it will be mentioned that the collision report schema or scheme will help up to for almost 2 hop distance from any transmitting node. Okay. Now the question is, do 11 broadcast it or unicast it or multicast it? Okay, look at this diagram which says 11th node, when there is a collision taking place, it's only responding to the node which has sent the reservation request, and then you are able to solve it. So this is the concept behind this protocol. Yeah, FPRP. Is it able to solve the hidden node problem to a little extent? The answer is yes. Okay, because you may be able to clearly access and find out that there is some node hidden there. Alright, you may be able to solve it to a better level. Now by doing one particular reservation in one particular slot, I have the flexibility of sending the same data or for other set of data, alright, at different IFs. That's the beauty. For example, let us assume that I have a data packet of, let's say, size, taking a simple example of 500 bits, and let's assume that in a particular frame, alright, let's assume Elijah was able to win the second slot. So what I can do is I can transmit in the next IF in my second slot. I can send the part of my data. And subsequent to that, in the next IF, I can still continue to post my data at the second slot. Are you getting what I'm saying? So when I block it, I can block it up to this particular frame. For the next particular set of IF frame, I have to do a little bit of reservation. So I can send 100 bits first, and then the next set of data, and the next set of data, but I have to only choose during my ISK. Okay. Now let's take a case where you are not successful. When I am not successful in a particular cycle, or let us assume the same case where we are taking here where there is a drop or there is a collision report. Go here, let's try to figure out what will happen if I try to reserve at a particular cycle. If there is a collision report, what will happen is I will attempt for the next cycle. If there is no collision report, then I go ahead and blocking it, and I'm correct. Now what is this packing and elimination? It basically gives you a frame which basically says, okay, I have reserved up to this point, now I don't have the data, and therefore I move out of the blocking of the reservation. Are you getting what I'm saying? Alright, so when I say I'm doing the elimination phase, that means I'm eliminating from my own reservation. So the concept is clear? Clear? Any doubts? Okay. So we will look at the next protocol, which is called as MACA with piggybacked reservation. We have already studied MACA, am I right? Now there is a new concept called we are doing some piggybacking up and then having some reservation schemes. Okay, so what is the fundamental concept? It basically provides real-time traffic support. So that means I can basically use it for real-time as well as non-real-time data packet. That's number one. Okay, and this is based on MACA-W protocol, which has a non-persistent CSMA concept or connection. Now what are the main components of this protocol? Alright, so MACA/PR, which is a piggyback reservation. You have a MAC protocol, a reservation protocol, and a QoS routing protocol. All this are bundled onto it. Okay, now when we look at this, you will really appreciate how this protocol really works. Okay, what is piggybacking? What is piggybacking? I'll take a simple example to make you understand. Now let's say that I have now finished the class. At the end of the class, alright, I ask you, when can we meet the next class? Alright, then you all say we will meet probably tomorrow at second hour. Alright. So what I have now done is I have reserved another slot for the tomorrow second hour at the end of my data transmission today. Are you getting what I'm saying? So that's a kind of a piggybacking concept. So the objective is to try to piggyback the reservation at the end of your communication of the data. So let's quickly look at this. A bit interesting to see how it is taken care of. Alright, so you have a MAC protocol, you have a reservation concept, and that's completely based on piggybacking reservation concept, and then you have a QoS routing protocol, and the QoS routing protocol is based on something called as destination sequenced distance vector protocol, which is called as DSDV protocol. And we'll try to understand this QoS routing a little later. Now try to understand what is this MAC protocol and how the reservation is done on a piggybacking concept. this is something like a packet transmission in a MACAPR. So I want you to quickly, closely follow what I'm trying to tell you, and then you can draw this if you want. Anyhow, this slide is made available to you. Okay. Okay. All right. So you have here something called as NAV for sender and NAV for receiver. So I have a sender here and a receiver here. All right. And I call it as a node allocation vector for sender and a node allocation vector for receiver. So basically each sender has a cycle. Okay, so you find there is a cycle here. Are you getting what I'm saying? So you have a cycle which starts here and ends here, and then you have a different cycle, and then you have a different cycle, and then you have a different cycle, and so on. So that means each time frame is basically divided into cycles. Okay. Now here it follows a concept called RTS, CTS, and then your data, and then your acknowledgement. Now let's look at how it really works. Now let's assume in this particular cycle, the sender sends the RTS. Now the question is, when will he send it in a particular time frame? Earlier you had certain slots, time frame for them to do it. So you will find here that the sender has to wait for a timing period. All right. And then probably send the request to send data. All right. And he sends the request to send data and then waits from the receiver end the clear to send. That means giving a clearance saying, hey, I am free that you are able to send it. Now how long it has to wait between sending this packet and receiving the CTS? One round trip time. So it has to wait for a one round trip time to figure out whether you are able to receive your CTS packet, clear to send packet. All right. So that forms one particular cycle. Is it all okay? Now, what is the contention for this? Or the, you try to send it, the request to send, and then you reserve a particular cycle. Are you getting what I'm saying? So assuming this, what happens is as soon as you receive your CTS, you reserve a particular part of a cycle for you to transmit the data to the receiver. So that is this cycle, and therefore we call it as this cycle is basically a reserved cycle. Are you getting what I'm saying? This is a reserved one. So you reserve a particular cycle for your data transmission. So it's very simple to look at now. You try to send an RTS, so before it tries to send an RTS, it looks for whether the channel is free. Are you getting what I'm saying? The channel is free, and if the channel is free, all right, and there is no busy or it's not busy, then you try to send the RTS, waits for one RTT, and then goes for the CTS to be the cycle. Now this is the data packet. All right, so you send the data and you find that there is a delay in receiving at the receiver side. So that's why reason you always put a dashed line with a little bit of inclination. All right, that means that shows that it is reaching there with a particular delay. That's what it means. Okay. All right. Now after sending the complete data, all right, there is an acknowledgement. Okay. Sending an acknowledgement, and this acknowledgement basically gives a confirmation, all right, saying when are we going to have the next cycle reserved for the next particular set of data. So you can try to exchange those informations in the last few bits of your data, and then probably also do a kind of a blocking of your reservations, and accordingly you continue to go ahead. So here in this example, you find that he has blocked for this cycle and he has not blocked for the cycle. Okay, so this cycle becomes free. So this becomes a free slot. But you find in the next cycle, it automatically starts to transmit the data rather than going for a sending on the RTS and CTS, because you have already blocked it for this particular cycle. Are you understanding what I'm saying? And then you have here, you find another acknowledgement, and then that also gives you a picture of what can happen in the next few cycles. Now the question is, how will each node know, alright, that this is how the reservation has been done? See, you getting it? How will this is one particular sender and one particular receiver. Now how does others know that I am blocking this for this particular cycle? Otherwise, what is going to happen is, at this point of time, somebody is going to send an RTS and then you are going to have a collision. Are you getting what I'm saying? Did you or no? Did you understand? Now you are, 5 of you are sitting here. Now let's assume that I am the sender and one of you are the receiver, maybe you. Alright. So I keep blocking it using RTS and CTS, and then I keep now sending the data to her. At the end of it, let's say I block this for the next cycle also. But unfortunately, during the next cycle, if someone doesn't know that we have already blocked you, he is going to put your RTS, and that's going to result in collision. Okay, so how do we really solve it? We basically solve it using a concept called a reservation table. Now how is it? Each node will maintain something called as a reservation table. Okay, that reservation table will help the node to understand that what are the reservations so far has happened for different cycles between different senders and receivers. Are you following what I'm saying? Okay, so at each node level it is maintained. So each one knows who has reserved for the next cycle, who has not reserved for the next cycle. Okay, now because we are trying to maintain a node, a table at a node, now it becomes mandatory that this table information need to be exchanged, or the reservation information need to be exchanged on a periodic basis to ensure that the reservation table is updated properly, so that there is no collision in the subsequent transactions. So you will find that we will have to do a periodic exchange of the reservation table, and that basically solves the hidden node problem, because now you are indirectly telling, alright, who are the nodes that are available and who is using which slot, or in a particular cycle and so on, and therefore it basically solves the hidden node problem. Okay, now in the beginning of this lecture, especially for this particular topic, I said it provides real-time traffic support. Okay, and then so that means we need to look at on two cases. When a real-time traffic is taking place, what's going to happen? When a non-real-time packet is going to take place, what's going to happen? So when a non-real-time packet is going to happen, all right, you can block it and start using it. There is not going to be a problem. Am I right? Okay. Are you getting what I'm saying? All right. So you know what data size that you have, because it's a non-real time. Okay, and then you have the data, and therefore you can push it up anytime. So you can see that this cycle is free. You can look at the reservation table of the node, alright, in your table, you find that the cycle is free, and therefore you immediately send your RTS and CTS, block the channel, and then start to use that. Now this particular protocol basically helps for the real-time packets, because real-time packets is what we can reserve for the future also. Let's say at every time 9 AM I need this packet to be transmitted, then I can fix up the cycle well in advance with the RTS and CTS and block my complete pattern of it, so that at that particular point of time the channel is completely made available for you to transmit your data packets. Are you getting what I'm saying? Consider a case where you do a real-time streaming. Alright, people say at 9 AM you have your real-time streaming done, it ends up at 10 o'clock. Alright, that's going to be a phase 1. and the continuation of that is seen in the next 9 a.m. or the next day, subsequent day. Are you getting what I'm saying? So that means you are now giving preference to all the real-time data traffic for that to be slotted and reserved based on a piggybacking concept. Once that is done, whenever there is a free slot available, alright, a node looks at it, the non-real-time data, so it has with him, and he wants to send it, he sends it when it is free. Are you getting what I'm saying? Alright, so let us assume that I wanted to do it at 9 o'clock today, tomorrow 9 o'clock, the next day 9 o'clock, and that's the reservation which I have done on a piggybacked reservation concept. What are the free slots available? 10 to 12 is free. Tomorrow 10 to 12 is free. The next day 10 to 12 is free. That means you can send those data which are not real time. You can fix it up, reserve it, and then start using it between 10 to 12 or 11. Okay? Alright, so we have now talked about a simple MAC with certain reservation on a piggyback concept. Now we need to understand that it also provides a very interesting feature of QoS. QoS is what? It's a quality of service. So this also helps in certain parameters of providing quality. Alright, when I look at quality and things like that, and this basically takes care of the bandwidth quality. Alright, now putting it the other way. Now my prime objective is to ensure that my data packets are not lost. Am I right? Data packets will get lost for two reasons. Number one, when there is a collision. Number two, when the bandwidth is very, very less. Am I right? Now let us take a case where the bandwidth is less. Okay, we know in communication, okay, in a particular network between two different nodes, you basically have different bandwidth available. Alright, so for example, all of 5 of you are here. Between 2 of your communications, the bandwidth may be higher, but for one to another person, it may be little lesser, and so on and so forth. Okay, so this MACA with piggyback reservation concept incorporates this QoS routing protocol also, wherein each node will broadcast something called as its own bandwidth availability and the hop distance with reference to each neighbor. Alright, for each path. Alright, so you have multiple paths. Am I right? Okay, so it transmits or it probably broadcasts its own bandwidth with a hop distance. So that means like this. I'm sitting here, and let's assume I have communications to all of you. Alright, so I have a dedicated communication from here to Sophia, I have a dedicated communication from here to you, and so on and so forth. Now I broadcast, alright, saying that my bandwidth with Sophia is this, my bandwidth to you is this, my bandwidth to you is this, and also say what is the hop distance that I have. So now when you are trying to compute a route for that particular data packets to get transmitted, I check for whether the bandwidth is available, a required bandwidth is available for transmitting that particular data through that particular path. If it is not available, what I do is I drop the packets. Are you all getting it clear? So that's how the quality of service is basically. Alright, so I basically drop it, or I particularly choose another path, whatever is the case, if the another path is available. Is it clear? So what is the summary of this? Basically this protocol handles the real-time traffic. Alright, and then it has 3 major components, which is MAC, reservation, and QoS routing. It maintains something called as a reservation table, all that, and then you try to do a periodic exchange of this reservation table in order to solve the hidden node problem. Alright, having said, it basically provides support for real-time traffic. Doesn't mean that it doesn't handle a non-real-time traffic. It handles it. So when does it handle? When you have a free slots available. Clear? Alright, so the next topic and here we will close. Alright, so this we will close. Alright, so this is the last protocol that we are going to look at under the reservation mechanism scheme. We have looked at around 6 to 8 protocols, I guess. Alright, so far. Alright, so we look at now real-time medium access control protocol. Okay, now it also provides a bandwidth reservation mechanism for supporting real-time traffic. Alright, it basically has two components, which is a MAC layer protocol and which has an extension of IEEE 802.11 and also takes care of a QoS sort of a routing protocol. Basically, it takes care of your end-to-end reservation with the looking at of the bandwidth components. Alright, it also maintains a reservation table. Alright, now the question is, you are almost covering up all that which I have covered in the previous topic. Then what is new here? The new here is there is no time synchronization required. So let's quickly look at how it is. This is what you find. Now in this protocol RTMAC, the frames are divided into super frames. Alright. Okay, so you have multiple super frames, and this is the node allocation vector for the sender, and this is the node allocations vector for the receiver. Now you find that this and this are not synchronized. Look at this. This super frame ends here, this super frame ends here, and so on, but you'll find that this super frame ends here and this super frame ends here. That means what? There is no synchronization taking place. Are you getting what I'm saying? But there is no synchronization taking place. How does it really, reserve it and use it is what we need to look at on a little logical perspective and little closer perspective. Okay, so the same concept, you have a sender and a receiver. Alright, and therefore in a particular super frame you send your RTS, which is basically for reservation, and then you have your CTS, and then you have one more which is called as an acknowledgement. Alright, so it sends an acknowledgement as soon as you receive your CTS. Once that is done, alright, what we try to do is we try to do a reservation. Am I right? We are doing this just for reservation. Am I right? Now, how are we going to do the reservation? We need to look at whether there has been any old reservation. This can be a fresh communication. Therefore, in that case, you don't have any old data. Alright. Now, on the other hand, we are doing a reservation now, which is valid for other super frames. Then that means, I have almost blocked it for two different super frames. Alright, so you look at this, alright, you will find there is a reservation here, which is a old reservation for node A, and therefore you find that you don't transmit the data during this old reservation time. On the other hand, look at here, you have a old reservation of node B, which basically comes up to this. That means this slot has already been blocked or reserved. Okay, so the mandate is not to send the data during this particular frame, during that particular time period, and not during that, but little later. Okay, so you find that the data, real-time data, is being sent at this particular point of time, and for which you get your acknowledgement. So you will find what's happening. You try to reserve it, and you do a reservation for a different, on the same super frame, but for a different time period. You try to book it here. So you try to book it this way, and then it books here. So in this case, this is the last part of the super frame, whereas here this is the initial part of the next super frame. You see what I'm saying? You're getting it? So you find there is no synchronization between the sender and the receiver. So here it also maintains a reservation table. Okay, it also exchanges the reservation table data according to all the nodes to ensure that hidden node problem is solved. and so on and so forth. So when you look at this super frame, what do you guess? This has been already blocked, or it's recently, it's blocking? Already blocked, because you don't have any senders RTS and CTS. So this is a reserved slot and this is a reserved slot at different super frames, and then you try to handle it. Now this can also supports the real-time traffic. So there are still free slots available, and you have any non-real-time data, you can transmit that during that particular. Any questions? Why is it called a super frame? Okay, that's a good question. We call it, name nomenclature, anyone can name it. Alright, you come out with a protocol, you have your liberty to call whatever that you would like to call. That's number one. Number two, there is a super frame concept brought in because this frame doesn't require a synchronization. Alright, so you say that is a super frame. You're getting what I'm saying? Because it basically doesn't have any synchronization issues. With all these cases, each frame have to be completely synchronized. Now let us assume a new node joins. Alright, he need not wait for the synchronization. Are you getting what I'm saying? It has to only wait for and be idle for a time, and then check for RTS, CTS, find out how the reservation is taken place, and then it gets the reservation table data because it's been broadcasted. Once that is received, you know when you can reserve it, and then you start reserving. So for me, I need not tune the clock as a new node join, already in order to synchronize with other nodes, and therefore we call it as a super frame because it's the best way of doing it. Alright, so any more doubts?